Good morning. Lecture 50. We are still continuing MOS models discussions. Let's have a quick recapitulation of what we have seen in the last lecture. So, last lecture we first discussed about the effect of channel length on the threshold voltage, and that was modifying this expression taking into account the charge sharing effect, where you know that this expression for threshold voltage, where gamma is called the body effect parameter, through charge sharing effect, gamma is modified to like this, which I discussed like this here, and this thing gamma multiplied by this entire quantity in bracket in parenthesis is nothing but our charge sharing factor we discussed earlier, where Ws and Wd are defined here as the junction depths, assuming flat junction approximation of the source and drain side. Ws and Wd are the depletion layer widths of the source and drain junctions respectively, assuming flat junction, flat and step junction. So no cylindrical junction approximation has been made here in these expressions. Okay. Then we consider the effect of velocity saturation, and this is a very important thing. We said that in the level 2 model, which is called also which considers the drain induced depletion, we assume that Qi is equal to 0 at x is equal to L dash, pinch off point, very close to L effective, very close to the drain. At x is equal to L dash, we assume Qi is equal to 0 at the onset of saturation. But this cannot be a very valid assumption. There is a false thing in this assumption. For analytical simplicity, we made such assumption. Qi cannot be 0. If Qi becomes 0, then the carrier concentration in the inversion layer becomes 0 and the current cannot flow. Therefore, we tried to make a better approximation, first by considering this small zone, small region of length delta L adjacent to the drain, where I said in saturation a very strong electric field appears because the entire voltage VDS is practically dropped across this delta L region, okay, because the channel has a relatively higher conductance and the drain region and source region is highly conducting, excepting the small pinch of region where the resistance is very high. So as a result, whatever voltage we apply is practically dropped across that very small pinch of region, and the electric field here, which is given by VDS, practically approximately given by VDS divided by delta L, is really very high. Usually it is quite above the so-called 15 kilovolt per centimeter. As a result, the carriers through this pinch of region are expected to travel in saturation velocity, which is called here Vmax, the maximum velocity of carriers. So the current density through this small region was written like this, with a standard expression, where Ni is the inversion carrier concentration in the pinch of region, Q is electronic charge, and Vmax is the saturation velocity of the carriers, the electrons in this case. Then, if I do so, you see that this approximation that E is it is related to the R. It is based on the approximation that R pinch off is very large compared to R, and delta L is equal to L effective minus L dash. Then we could write the ID sat expression by multiplying JD sat, which is this, with the cross section. Cross section is the width of the channel W multiplied by the DI, the thickness of the pinch of region, which I called I. I means inversion. Actually, this I we have used, but you see that it is semi-inversion kind of region. It's not just out of inversion. So I say that thickness of inversion layer at pinch of region, but by this I should not mean that it is inversion layer in the, it is a very feeble inversion layer, not a strong inversion layer, a very feeble inversion layer at the pinch off. Whereas at the left of pinch off there is strong inversion. To the right of that pinch off there is in plus drain region. Whereas in the over the pinch off region we call it a very feeble or very feeble inversion layer. Its thickness di is usually larger than the inversion layer thickness, which I indicated earlier. And then this ID set finally can be written by combining this. You see that di multiplied by ni is nothing but qi, the charge in that point, the inversion charge. So ID set is given by this, and ultimately qi is therefore is this. Now where qi is this is equal to this, and ultimately we from this equation qi is obtained as ID set divided by W into Vmax. And I said, what is the procedure of calculating that? I said that the expression for VD qi in terms of VDS and VGS was equated to 0 earlier to derive the, to get the value of VD set. Now instead of writing it 0, I write this value. This value is obtained initially assuming an ID set based of qi is equal to 0 approximation. So I get this. I solve the equation to get VD set. And from that VD set, using the linear region expression, I get ID set. Once again, I iterate. And through reiterations, the number of iterations, we finally get a value of VD set and ID set which converge reasonably. And that's how we get the more accurate value of VD set and ID set using the eliminating the approximation that qi is equal to 0 at x is equal to L dash, which is not a very valid approximation. Whereas in now the lambda parameter, which is nothing but the channel length modulation parameter, was further modified by taking into account the velocity saturation using this equation. It is due to Baum and Binecking, where you see that xd, which is equal to root over twice epsilon base by qna, is further modified by introducing the term n effective, where n effective is a substrate doping coefficient. And I told you that by adjusting the n effective value, the IV characteristic can be fitted well with the experimental value rather than assuming n effective equal to 1, which was demonstrated at the end of the last lecture through a number of curves obtained using level 1 and level 2. In level 1 and level 2 for two values of VGS. VGS is 3 volt and VGS is 5 volt. And L effective is, I think this for this L effective value, did I mention, is of the order of 510 micron. And then we have seen that for one, which is for level 1, where lambda has been assumed to be 0.05 volt per unit volt, and level 2 is this one. It assumes qi L dash equal to 0, and this number 3 curve is qi L dash is equal to 0, but n effective equal to 1, which is a little bit odd curve. To restore it to a value which is closer to experimental data, now in number 4, Vmax is the same, but n effective has been modified from 1 to 5, which gives a better fitting. I ask you to give a thought to this. What is the justification of using n effective? I do not know whether you thought of it or not. Let us now switch over to the today's continuation. So we are still continuing level 2. In level 2, the channel width effect of channel width on VT called narrow channel effect. VT, I call it channel width vis-a-vis VTH, this dependence is considered in the same fashion as we have discussed earlier. You remember in device physics lectures, we said that when we look at the device cross section perpendicular to the channel, we look at the device cross section perpendicular to the channel length, it looks like this. This is a gate oxide, these are the field oxides, and we have a gate, overlap gate here. Okay, this is your VG. We call it VGS now. So channel is confined, but when you apply a VGS now, the so-called depletion layer is spread laterally like this. Whereas in one-dimensional approximation, we assume then when you apply a gate voltage here, the charge is induced only over this rectangular region or rectangular parallelepiped region. It is the L direction. This direction is the channel length direction. This is perpendicular to the channel length. Okay? This is the cross-sectional view perpendicular to the channel length or along the width direction. Okay? And here I told earlier, because of this fringing of electric field at the edges, the depletion layer boundary is just not like this, but is semicircular or maybe elliptic. Actually, it should be obtained by a good numerical or two-dimensional Poisson's equation solution. Roughly, we assume to be semicircular or quarter circular. These two regions are quarter circular. So we said that the charge contained in this entire region occupied by the depletion layer divided by the charge contained in the rectangular region just below that gate, this ratio, we call it a charge sharing ratio for narrow width effect. And this is more than 1. And as a result, the narrow width effect increases the value of the threshold voltage. Whereas the short channel effect reduces the value of the threshold voltage. The narrow width effect increases the value of the threshold voltage. This was discussed earlier, and I've spoken of the charge sharing factor and etc. The different kind of approach. The physics which was discussed earlier, you will find they're more used in level 3, but not in level 2. What they do the same thing, but they write an equation for VTH on the basis of the charge sharing in this particular fashion as follows. You see that what has been done here, that gamma dash is here, and that gamma dash takes into account the effect of that short channel which I've considered earlier, whereas this additional term is, this is an addition over above the that when this delta is equal to 0, this term is not there. So the expression for the threshold voltage valid for taking into account short channel effect, that is how it is gamma dash, is there. But addition of this last term brings in the narrow width effect also, where delta is a parameter called width effect, narrow width parameter or width effect parameter. Delta is equal to 0 is normally default, whereas delta is equal to 1 is a typical value. However, you have to play with the value of delta. All these parameters, you see that so many parameters are being gradually added in the level 2. In fact, you have to play with all these parameters little bit for fitting with experimental curves. It is a very tedious job, but that is what is done in practice. It is a very tedious job. But once you do it with, say, 1 week's hard labor, then you can blindly use those parameters for the technology which you have developed in the lab. Suppose I have developed a MOS technology with 1 micron. I make several MOSFETs with different sizes, measure the IV characteristics, then fit them with one of the available models, maybe level 2. So while fitting, you will find that so many parameters already you have discussed in level 2. Today, now I have introduced another parameter. Okay, you have to first start with some default values, which is physically things. That means delta is equal to 0 means no narrow width effect. Okay, so it's like this. You can always start with the default values and plot the graph, compare with the experiments. But then, seeing with based on your experience and device knowledge, device physics knowledge, you can now play with the different parameters in a very systematic fashion. It's not an easy task, let me tell you. It's a rather difficult task. You have to have sufficient device knowledge for doing that. They are the physics of device courses, which have, as a backup course I have already offered, will help you. You cannot do it blindly. You have to adjust the values till we get the closest match with the experiment. Then these values you store in your memory, in your computer, for the different parameters which you have obtained. And they say, so 1 micron technology which you have developed in the laboratory, and using that 1 micron technology, whatever circuit you now make, the devices now can be simulated using level 2 or level 1 or level 3, whatever is applicable, in this case level 2, using the set of parameters which you have extracted with lot of hard labor. Because you had to do some experiments, you had to make the device characteristics, then you have worked hard to fit your curves obtained from these models by adjusting the values of these parameters. And this cannot be done arbitrarily, then you will be in totally gone. If you just arbitrarily go on varying the values of these parameters, you will be totally offset. What has to be done? You have to apply your own sense based on the device physics which you have developed so far, and finally try to get a curve which is the closest as possible with the experimental value. Once you get that, you can assume the same set of parameters now I can use for the design, for simulating the circuits, with where only thing will vary, that is the geometry of the devices. Otherwise, the basic process remains the same. For all MOSFETs, whatever you fabricate on the chip, the fabrication process, sequence, the parameters, they remain the same. Only geometry changing. Maybe some MOSFETs which have to handle higher current, I have a bit larger area, W and usually W, smaller current, a smaller W. But then it is a digital design, then you have to maintain the W by L ratio criteria. If it is a CMOS, you have to consider both PMOS and NMOS together. But you have to separately validate your data for P MOSFETs and N MOSFETs. You cannot use the same data which you have used for N MOSFETs for P MOSFETs. So you have to do two sets of experiment for P MOSFETs and N MOSFETs. Independently feed the data for PMOS and NMOS, and thereafter only you can. It's a tedious job, and that is why it is so much time consuming. Initially it takes a lot of time. Once for the particular technology you have settled it, then it becomes very easy because already you know spice blindly use spice then. Now so far we have considered only the DC, is it not? The ones which you have so far discussed, they are all DC characteristics. For the given values of VDS and VGS, we get the value of ID. That's the only thing which I have, but that I have tried to get as accurately as possible. All these attempts I have made. But when you apply an AC signal at the input, or you apply a transient, as happens in the case of a digital gate, 0 or 1 at the input, then what are the responses? How the currents and voltages at the different branches and nodes respectively vary with time because of a response, because of some time varying input signal, okay? And for that, in addition to these DC characteristics, whatever we have generated, I have to also add the AC. But AC normally here, it is only the capacitances which are important. Because in these device structures, they are usually very small. They are usually very, excepting for the interconnect lines. The inductances do not come into picture, or rather they play a very insignificant role. The inductances. The only thing so far as AC or transients are concerned are the capacitances. And MOSFET being a 4-terminal device, okay, source, drain, gate and body. So there are so many capacitances, inter-electrode, junction and so on and so forth. And I must be able to model these capacitances precisely. And once I model these capacitances, then it is not so difficult to simulate the whole thing, even in the transient case. So let us first see that how the gate capacitances are modeled. These gate capacitances are predominantly MOS capacitances, but then there will be some depletion capacitance, depletion layer capacitances involved. This is due to Meyer. First case is accumulation. VGS is less than V on. It could be VTH also, but V1 is more precise thing. VGS is less than V1 or VTH minus 2 phi P. That is my condition for accumulation. And for that, the capacitances between the gate and the body. GB means capacitance between the gate and the substrate. B stands for body. Please remember, G stands for gate, A stands for source, D stands for drain, B stands for body or substrate. Okay, this is normally simulated as COX plus CGBO L effective. Just looking at these equations, can you tell me that what are the significances of this CGBO, CGSO? What are they for? CGBO, CGSO, and CGDO. Where please note that COX is the total MOS capacitance that is equal to COX dash, the per unit area value, multiplied by the area of the gate. So COX is this. Okay. What is CGBO, CGSO, and CGDO? These are called overlap capacitances per unit length or per unit width outside the channel. CGBO, sorry, CGSO, overlap capacitances per unit channel length actually, or width, whatever is applicable, outside the channel. Can you tell me what is this? Actually what it is? Can you visualize? Can you visualize it? This capacitance between gate and body. You see that when you remember this diagram, check this diagram, yes. When I deposit the electrode, okay, this is the so-called gate region, perpendicular to the channel. Source is one side, drain in the other side. Above the diagram may be source, and below the diagram may be drain. Okay? Alright? So between gate and body, there is some extra things beyond, that this COX is what? What is COX? What is COX? What is COX? COX is the capacitance under the gate. Under the gate means considering the rectangular region. It is COX dashed multiplied by the area. What is this area? This is W and that is L, where the gate oxide thickness is only TOX. Outside that, the gate oxide thickness is T field, thickness of the field oxide. Okay? So COX dashed multiplied by WL effective means it is the capacitance of this so-called rectangular of only the gate oxide region. But there is some overlap here and here. So between the gate electrode and the substrate, there is an overlap along the channel length on either side, this side and that side. Okay? So what is the significance of CGBO? CGBO is this overlap capacitance taken two together per unit channel length. So if we multiply it by the channel length, we get the total overlap capacitance. So COX is the capacitance of the actual channel region between the gate and the substrate, and CGBO effective is the overlap capacitance due to the overlap on either side. Overlap because you know that firstly you see that so far as gate this side is concerned, you see that what has happened, you cannot align this thing exactly. There are two things happening. One is the fringing field effect. Secondly, the gate electrode is a separate lithography, isn't it? You cannot make the metal deposited exactly on this slot. You have to give some extra because of the mechanical alignment, okay? And that will give you some extra overlap. That is why it is called overlap. Actually, overlap means it is due to the fringe field plus overlap taken together. One is even if there was no overlap, there will be some extra things here. That is due to the fringing of field. But if there is an overlap, there will be an extra capacitance. That is particularly reflected. That is why the general name of overlap capacitance. Same way, we can say that CGS is equal to what? Between the gate and source. When in accumulation means the channel is totally absent. Channel is totally p-type. So there is a little amount of gate overlapping over the source region, and that will give you some capacitance whose value is CGSO per unit width. Now you have to consider width. When you multiply it by W, then this gives you the total capacitance between the gate and source sink. So gate and source due to the overlap effect. That has to be minimized. That has to be minimized. But so far as gate source is concerned, it is not that important. But between gate and drain, it is very important. Similarly, in accumulation, between gate and drain, it is the same CGDO. CGDO is the gate to drain overlap capacitance per unit width multiplied by the width gives you the total gate to drain. Please note, now the channel is absent. The conducting N plus layer connecting source and drain is absent in accumulation. So this is the model they use. Then consider the depletion region. Here V on minus twice phi p. That means usually we say that it is VGS less than VTH. Up to that point, I am calling it depletion region. Then CGB was modeled by Meyer as follows. You note that here for the depletion region, CGB expression has been modified. Earlier it was COX plus this. Now it is COX multiplied by this. What can you tell me what is this? What is the significance of this? As we apply now a gate bias which depletes the channel, so there will be two capacitances in series. One is COX, the other is C depletion. So these two will be in series. Therefore, this one is that total series capacitance simplified form, in model simplified form. Actual equation a little bit more complicated. That is how Meyer did it and find more or less it is accurate. So it is COX multiplied by this. This taken together is nothing but the total capacitance comprising the oxide capacitance COX and depletion capacitance CD in series, and that is voltage dependent, VGS dependent. So that is this. And the other term is as it is remaining. CGS between the gate and source, earlier it was only CGS, so because then what we assumed? In that case we assumed that this the channel is totally absent. So the channel region was not considered at all for calculating the capacitance between gate and source. It was only due to the overlap. But remember, gate is a big electrode, and those source at one end, but sometimes source can also be extended electrically below the surface. Why? Because as soon as you apply a VGS which is more than 0, 0 means which is more than VON minus twice phi p, but at the same time less than VON, that means channel is depleted. So what is going to happen? Surface potential near the source is increased, and as a result the barrier at the surface source is reduced, and that causes electron injection. Source injects electrons, maybe it's not very large in number, but they inject electrons from this source injects electrons into the substrate, but in the substrate there is a field force which push the electrons to the surface, and these electrons are all located at the surface and forming a so-called weak inversion layer because we are still below VON. But this weak inversion layer electrically extends the source from the source end towards the drain. But because it is below VON, till that full channel is not total. So what is going to happen as a result, that the CGS value in addition to that CGS OW, which is the overlap capacitance, another component is added, which is this. It is modeled like this. There are some theoretical derivations behind them, but ultimately simplified is like this. And what about CGD? CGD has been kept as it is. We are assuming that because we are still below VON, the channel has not been fully formed, therefore drain remains isolated from the channel, and as a result what is only the overlap capacitance that dominates. That is why in the depletion region they simulated CGB, CGS and CGD. Like this is the logic behind. Then saturation region. For which VGS is like this. VGS is more than VON but less than this, and that is the so-called saturation region. Saturation means that there is a pinch off region. In most of this channel is well inverted, excepting a region close to the drain which is pinched off, that is saturation. Under this case CGB is approximated as CGB is equal to CGBO but the COX term is practically not there. What can be the significance of this? in saturation region. And so what? Body actually gets isolated because the inversion layer, the body is electrically screened from the gate. So the other effect, it is only the lateral penetration, that means the so-called lateral overlap. That is a very approximate way of handling. Is not really correct, let me tell you, but this is how they model it. And CGS is they modeled at 2/3 of COX. 2/3 of COX. That means this term has been assumed to be 0 plus CG. What is the significance of this? In saturation region, they say that not the as if from this gate, from the source, the channel is, because it is between the gate and source, isn't it? The inversion layer has formed. So electrically, the source region, you have contacted at source. There has been an electrical thing extending via the channel, through the channel, up to the drain end. Okay? But drain end, there is a pinch off because it is saturation. So that capacitance should be actually COX, but it will be little bit less than COX, and they have approximated it as 2/3 to 2/3 of COX, not COX. There is some mathematical derivations behind this, but anyway, this is how they approximate it, plus CGS OW. Okay, and finally CGD is the same as till now. The CGD, there has not been any change, because I am assuming, because pinch off has formed till the drain is isolated. Lot of approximations are there. Then linear region. Here CGB is approximated as CGBO L effective. CGS is COX. I am giving you these expressions because they are standard available. I don't think you have to remember them. Just try to understand. Sorry. don't like it. This is BTH or beyond, whatever you call it, does not differ much. Whatever expressions we have written so far, that can be finally crystallized in the form of these three graphs. Okay, and you have to you can try to explain out how these capacitance they are varying like this. By here it is 0 means that it is very small. The overlap capacitances etc. is very small. Assuming that it has been assumed to be 0. 0 means very small compared to COX. Actually, it should not have been shown, but I have taken from a reference, the same reference, Antignotti and Mosabrion, his book, and they are just shown like this. Actually, it depends. It depends on the technology. The smaller the devices, the maybe little bit relatively more will be the overlap because of the alignment difficulty. That is why I told you that today the technology aims for self-aligning kind of things. Most of the steps they want to make self-aligning instead of separate alignment, so that the alignment is more precise automatically. Anyway, these curves you can try to fail. One thing perhaps you know that it's a very complex situation. When you think in terms of circuit simulation, so you are applying say nodal analysis and loop analysis, whatever approach you feel convenient, and there so far as DC part is current in a branch, therefore now consists of two components. One is a DC component, the other is a transient or AC component. DC component because you understand, say take the case of an inverter circuit, simple inverter circuit. Simple inverter, very simple inverter. So if I apply a time varying input, and if I assume that the input is varying slowly, so that the ID and VDS etc. they are going through a what? Going through some DC time, and there is no dynamic thing. That means if I assume Vi is moving slowly, that means DC equations are valid. Whatever current voltage equations I have derived, they are derived. So what I can do, by assuming that Vi is changing from 0 to some VDD or V high slowly, I can always calculate how VO will change with Vi. Do you follow? If Vi changes from 0 to 5 volt, and this is suppose also 5 volt, as Vi changes from 0 to 5 volt, I can also calculate how VO changes from roughly 5 volt or 4 volt towards 0. That will be a calculation based purely on DC analysis. I assume the same current voltage equations. So from that, suppose now I assume that Vi is a particular waveform. I have applied here Vi whose waveform is something like this, not a sharp one. It may be a ramp type, that is sweep type, or it may be a slowly changing type. It depends on you. You apply some time varying input. For this time varying input, now I am interested how exactly VO will change with time. Now, when Vi changes from this point to this point, when Vi changes from this value to this value, maybe 0 to 5 volt, slowly, calculating how VO changes from that VDD to, or it may be VDD minus VT, depending on whether the load is in saturation or not. If the load is